Okay, gentlemen, we're going to look at the first couple things we had talked about in our Desmos activity, right? So you had homework on this. It was homework 2.6. I think some of you found it a little difficult because we didn't get through every slide in the class that we had last time. So I'm going to go over the things that were important for us to go to have to do that homework fully. First couple were just the vertical line test, but the second three problems were based on what kind of discontinuities do we have. And I think some classes got through it further than others. So I'm just going to post up the summary that was the last slide of the Desmos. So I'm going to leave this here. I'm going to write down here. This was slide number 21 from student.desmos.com, and that was that intro to continuity. Intro continuity. Right, so in one of your lab classes, I had kind of gone over this, but just I'll summarize it. I'll do a couple examples, and then we'll kind of get into some new stuff. So the domain of a rational function is found before you reduce, right? So we had talked about how that's like your number one first step is the domain. Then the x values skipped in the domain are the values where the function is discontinuous. So the discontinuities are directly related to the domain. Okay, if we cancel out a factor, that x value is removable. The remaining factors, only the ones in the denominator, we call infinite, forever problems. Right, and another name for them is vertical asymptote. And we're going to kind of talk a little bit more about asymptotes today. Okay, so just to go through, here was my initial function, 2x squared minus 13x plus 15. We took this and we factored it to 2x minus 3 and x minus 5. And that was what we had done on the first slide. And I asked you what were the roots. Here they are. These are my roots. And I said, what are these as ordered pairs? The x-intercept as ordered pairs. Well, it's 5, 0 and 3 over 2, 0. Because this is the x value that will make that fraction, that polynomial equal to 0. These are the x values that will result in 0. If I plug 5 in, I will get out 0. And that's the whole idea here, is when I make this equal to 0, like our test 1.3, everything was set equal to 0 because we had to factor and solve. Solving, we had to do when e was equal to 0. I asked for the y-intercept, and we said the y-intercept here was that 15. Plugging in 0 for x will give me a positive 15. And we said the domain of this guy was negative infinity to infinity. That was our first thing. I want to go through that just so we can see that this is what it factors to, and we're going to use this a lot. Okay, a quick go over. We have this as our first function we did on our slides in Desmos. And we see, I think it was actually the other one, 2x minus 3. And we see here that I have my regular polynomial and now a new denominator. So my first step is take the domain, and my domain is just focused on the bottom. The only thing I'm trying to do is figure out what makes this fraction equal to 0 on the bottom. That would be 3 over 2, and I'm skipping the one number 3 over 2. Because I skipped the number 3 over 2, I know that this is a discontinuity somewhere. This is a discontinuity. If I'm skipping a number, there's a reason, and that's because it messes up my graph. Okay, now my next step would be, well, let's factor the top, which we already know what it factors to, because we've seen it a bunch. Okay, and I know I'm going to cancel that factor, so I'm just getting an x minus 5. So that's what I simplify to. That's what I reduce to. It's just this x minus 5 is my reduced function, reduced. Okay. Since I was able to cancel out my denominator and be left with x minus 5, which does not have a denominator anymore, now it's just over 1. If I was able to cancel that means that I have a removable discontinuity. There's my abbreviation, removable discontinuity at x equals whatever the value that comes from this factor, which is our 3/2. Okay? And what this means for me graphically is I will have my reduced, here's my -5. I'll have my reduced function, except at 1/2, or at 1.5 rather, so 3/2, I will have a whole. And that'll be exactly at 1.5 or 3/2. Okay? So let me summarize it again. So we have our rational function, first step domain. Skipping the number 3/2. I do that first. I just look at the bottom, do it. That's a discontinuity. So I factor. Oh, I'm able to cancel it. That means it's a removable discontinuity at the x value that comes from that factor. My reduced function is what my graph will look like. Slope of 1, -5 is my y-intercept, except at 1.5, 3/2, I have a hole in my graph. And that's what a removable discontinuity is. Okay? So if you want to write a small summary, is if I can cancel out the factor, that x value is my removable discontinuity. Now that's summarized up above, so we don't need to write it again. Right? I wrote that up here. The removable discontinuity is whatever x value we cancel out. Whether it's on top or bottom, it doesn't matter. Obviously, it's kind of both here. If I have the exact same functions numerator, and I make the denominator x -5, I'm going to do the same steps. First is domain. This time, the one value I can't use is the number 5. And that comes from here. Once I'm skipping a value in my domain, that means I have a discontinuity somewhere. Look at my numerator, I factor that. Look at my denominator. I'm able to cancel out the x -5 and be left with a reduced, simplified 2x -3. And that tells me that at the value x -5, I'm able to cancel that, so that means I have a removable discontinuity at the x value, x equals 5. My reduced function will be what my graph looks like, except there'll be a hole in my graph at the value of 5. So if I'm looking at this graphically, I'm going to see I have, here's my -3, here's my slope of 2x, here's my 2x -3 line. Right at 5, x equals 5, there's going to be a hole in my graph. Because I had a removable discontinuity, I was able to remove it because I canceled it with part of the numerator. Okay, that should be the review part. So hopefully that didn't take too long. Now let's look at what happens if I flip this. Only a few of my classes got up to this point, but 2x -3 over 2x squared minus 13x plus 15. So this is the second example we had just flipped over. This is the second example we had just like reciprocated, just flipped over. Step 1 is still my domain. A little more complicated because let's say we didn't know how to factor this. We'd have to factor the bottom. And then say, okay, so that means I'm skipping 2 numbers now. 3/2. And then I continue onward up until 5. I skip 5. And then I continue onward to infinity. So I'm skipping 3/2. And then I'm skipping 5. So now in this function, I have two discontinuities, which means I should be able to name these two discontinuities. Maybe they're both removable. Maybe they're both not. Maybe one is. Let's see. So now that I've factored it, let's take a look at what we have. Here's my factored function. Crossing out my 2x minus 3's. Oh, that means that there is a removable discontinuity at x equals 3 over 2. Removable means cancelable. I canceled it, so I call it removable at the x value that comes from that factor. Okay, now this 1 over x minus 5. Okay, that's what I simplified to. But that x minus 5 can't go away. I'm stuck with an x minus 5. That's got to be there. So here's my reduced function. So that x minus 5 factor doesn't go away. Up here, it was like the top of a fraction. Right? So this is really like over 1. This is really like over 1. So I just had a line. It's linear. This, I just had a line. It's linear. This is 1 over this x minus 5. So now my graph looks different. I'll throw it in Desmos for you. My graph looks like this. Well, at 3 over 2, I'm going to have this whole thing. So I'm going like this. And then I'm bending away from this value of 5. And that's because I'm not able to remove the x minus 5. So that means at the value that comes out of that factor, the 5, I have this infinite forever problem. This is a problem, but I fixed it. I removed the problem. This is a problem, I didn't remove it, so it stays. 5 is a forever problem, and my graph is bending away from that gross number 5 I can't use. But I was able to remove the 3 over 2. So that means somewhere over here, there is a hole in my graph, and that's exactly at the value 3 over 2. Removable means there's a hole in my graph at that x value. When I have a leftover, a remaining factor or factors in the denominator, we call that an infinite discontinuity. So now we get over here and we say, okay, I skipped the value 5. I wasn't able to make it go away. It stayed. And my graph totally skips that value forever. That's called an infinite discontinuity at x equals 5. We also call infinite discontinuities. They are the same thing, renamed, different name, called a vertical, which we see here. And the name for the bending away, asymptote at x equals 5. So an infinite discontinuity is a vertical asymptote. An infinite discontinuity is a vertical asymptote. They are interchangeable. It's like Jack and John, right? Dan and Danny. They are interchangeable. And that is what the name of this dotted line that shows my graph is bending away from 5, because 5 is a problem. I can't plug in 5. It'll make my denominator 0. So I bend away from that value. There's a break in my graph, a discontinuity. I bend away and I'll never cross over. It's like Pac-Man. I jump down and then I just reappear up here. It's called an infinite discontinuity or a vertical asymptote. One more. Let's do the same function one more time. And now I put it over, under the x minus 5. I'll do this a little faster because we had a longer discussion for the first one. Step 1 is domain. Obviously, I have the same factors, and I just did this, so my domain is the same. 3 over 2 I skip, and 5 I skip. 5 I skip. Okay, I'm skipping 2 numbers in my domain. That means I should have 2 discontinuities times 2. 2 of them. Well, let's see, what am I able to cancel out and what am I not able to cancel out? Denominators only. That's really my only problem with fractions. So that's the only times when I gotta really take a look at it. My x minus 5s are gonna cancel. So that tells me I have a cancelable, which we call removable. I fix the whole discontinuity at the x value that comes from that factor, 5. Now this will simplify or reduce to my 2x minus 3, but it's under 1. So I have a 2x minus 3 as my denominator that's under 1. That can't be reduced or gotten rid of, so we call that an infinite discontinuity at x equals 3 over 2. This is probably something I asked you to find the domain of at some point on a test or quiz, like 3 over and something kind of simple. I skipped the number 3 over 2, and we just knew that was my domain. I'm skipping the number 3 over 2. But the reason being is my graph is bending away from that value. If I plug in 3 over 2, I get 0. I can't use it. I gotta completely throw it away. An infinite discontinuity is the same thing as a vertical asymptote. So we will always write both 3 over 2. A infinite discontinuity is a vertical asymptote. They are the same. So I'm just writing it twice. Okay? That's just a little summary of what we had done, what I wanted to get through totally with my discontinuities. So we have 2 types, removable and infinite. And again, removable is if we're able to cancel it. Infinite is the denominator ones that we can't cancel, and we also call them vertical asymptotes. Okay, and I'm looking down here, and that's the last problem we did. We kind of summarize the whole thing. We see our 2 skipped numbers in my domain, and we named both of them. Okay, so take a look at this, review this, and we're going to have another video talking about other aspects of functions.